can sort of like tweak it enough. There's no online manual about this, by the way, so I was just like doing random experiments and figured it out. But I can use the camera from iMac and then the external view from iPad and slice like very good. So we are at 10:02. So let me introduce you, and then so it's my distinct pleasure to have John Wieting as a speaker today. He's a PhD student at CMU, working with Taylor and Graham Newbeck, and previously also worked with Kevin Gimpel, actually still publishing with him, it seems. And I don't think we met before in person, but I've known John's work for a while, especially his ACL paper on large-scale translation, paraphrase learning from translation. Recently, in one of our EMNLP submission, we also cited that paper and compared against it. So very cool work that we've been following. So I am very excited to hear more about this today. And John, you can take the floor.
Well, thank you, everyone, for having me today. So yeah, my name is John Wieting, and today I'm going to talk about my work on the learning and applications of paraphrastic representations for natural language. So representation learning, as many of you in the audience know, has had a tremendous impact in machine learning and natural language processing, especially in recent years. Learned representations provide useful features needed for downstream tasks. They allow for the models to incorporate knowledge from billions of tokens of text. And this all results in better performance and generalization on many important problems of interest. As depicted in this figure, I will discuss learning representations for different granularities of text, from subwords to words, and finally to sentences, which has been like the focal point of my work. Here's just a quick outline of the talk, trying to cover everything in a reasonable amount of time. I'm going to first kind of go back in time a little bit and talk about word embeddings. This is my earliest work, but it kind of set the stage of how things would play out. Then I'll talk about sentence representations from simple models to deep models. And then I'll move to the multilingual setting. Again, going from simple models to the bigger, deeper latent variable models. And then I'll close with an application towards fine-tuning neural machine translation systems. And then I'll discuss some future work and some future ideas I'd like to pursue in both the near and medium and long future. So word embeddings. So here are glove embeddings in like 2 dimensions. They're a very famous set of word embeddings, and essentially these are all points in space, and each point in space corresponds to a word. And what you can find is that words with similar meanings are near each other. But one issue with this is that it tends to conflate different relationships between words. You'll see things that are co-hyponyms, such as like man and women. Even things that are antonyms from each other are near each other in this space. And so one motivation for much of my work has been on refining this space, because we want nearest neighbors of words to be paraphrases. So essentially, we can kind of go from the figure on the left to the figure of the right and separate things out according to their semantics. So how can we do this? Well, we started by just thinking that we would need to incorporate some paraphrasing information into representations. Basically, we hypothesized that at least 2 views of the same underlying concept are needed. Otherwise, words of similar context will be closer together in the embedding space, which allows for these, this clustering of very related terms, but not semantically similar terms. So data with multiple views can come in many forms, from paraphrases to bitext to even multimodal data. So as a simple start, we just talked about like paraphrase data using the Paraphrase Database, which was It's a very strong resource, essentially created by pivoting over bilingual text. You find foreign phrases that are mapping to, you find English phrases that are different that are mapping to the same underlying foreign phrase. And that's how you can kind of extract automatically these paraphrase snippets. Just here's some examples for the word case. So it's a little noisy, but we made it like the focal point of ours because it has strong coverage compared to something like WordNet. And then we need an objective function too. So now we have some data. We basically have this x1 and x2. These are pairs in PPDB. And now we want to have a model and we want to have an objective function. So here, like the G's are these encoding functions, which I'll talk about more later. Essentially, what they're just taking in this case are word vector, and they're like a word in English, and they're just mapping it to a vector. And all we have to do is we just sum over our pairs in our paraphrase database, and then we take the cosine of the positive pairs, so just x1 and x2, and then we take the cosine of a negative pair. So we somehow extract a negative example, T1 for x1 and T2 for x2. And then we basically are just optimizing to push, our positive pair away from the negative pair plus a margin. So this is just a max margin contrastive loss. And the performance, despite the model being fairly simple, is quite strong. So here, again, this is all very ancient work, but like at the time, people have been starting to like focus on this problem, and we compared quite favorably, despite only using 100 or 200,000 pairs over things like retrofitting, which was something that was at a similar time frame as ours, and it did solve this nearest neighbor problem. So you can see like love nearest neighbors on the left and Paragram, which is what the name of these embeddings are, on the right. Essentially, we can kind of get around things that are like these co-occurrence statistics that are kind of messing up the space. So example, like on the left, you can see things like rampant, but it's oftentimes the noun that rampant modifies is usually included in its nearest neighbors, just things like corruption and greed and epidemic and racism. And then on our right, we tend to stick to just adjectives and things that tend to be synonyms of rampant. So these word embeddings, again, this is kind of a simple starting point, but this is, it kind of sets the stage of the theme of a lot of my work, which is basically trying to find two views of some semantic concept and then proposing objective functions and encoders to create these, like what we call paraphrasing representations, focus mostly on this semantic similarity. Like these embeddings, they have found many uses in NLP literature over the years, things from dialogue to entailment to adversarial examples, and even some more. So that's word embeddings. And now I'd like to move to sentence embeddings, which require different strategies. And it's a little unclear if this is even possible to do this as well as you can for word embeddings, since sentences are far more complicated. And you have to reflect, the syntactic structure is also very important, which you don't have to worry about in word embeddings. So sentences, you can embed them and you can create a space, and whether the space is useful or not is a separate question. But with our space, just as this space as we tried, it does tend to cluster the semantics, pointing that this is possible to some extent to just create this space of sentences where sentences with the same meaning are closer to each other than those without. So basically, why we want to learn these. Initially, actually, our focus wasn't so much on any application. It wasn't about creating good paraphrasing functions. It was really focused on like studying compositionality of language. At the time, you were thinking about how can you compose a sequence of words into a representation, and then how do you even know you did it correctly? Like, how can you judge between one set of representations and the others? And so what we always thought was that, well, if you do a good job on this, sentences with the same meaning should be near each other. That's like our core definition of whether you've created a good sentence embedding space. And this should be robust. This should be agnostic to the domain of the text. So that was kind of the underlying, our underlying research goal. But as a side effect of this, you do get some nice properties and applications like paraphrasing. So our evaluation reflects this. So for sentences, we basically collected a bunch of semi-val semantic similarity datasets over all years possible. And so we proposed like this evaluation, but with a twist. So these evaluations had been used for years, but people trained their models on it. And they would use features and things like SVMs and stuff like that. Because this is largely pre-neural. But we propose more like just a zero training, unsupervised setting where you train on some outside data, and then you just use these strictly for evaluation, no fine tuning or anything. And the whole point is that can you create representations that do well in these tasks, hopefully even as good as systems that actually use the underlying training data. And one nice thing about these tasks too is that they cover many different domains. So here's some examples where the blue one is a positive example. These express the same semantics, but it kind of shows the difficulty of the problem where there's not a lot of lexical overlap, but they do share the same underlying meaning. And the red is a negative example where the opposite kind of occurs, where they share a lot of lexical overlap, but you know, in this case, there's actually a contradiction. So they do not have the same semantic meaning, and that's a very low score. So then these are evaluated with, you know, you just try to match the correlation between the human and the and your system outputs. So again, you know, these cover many different domains, things from tweets, to news, to glosses, to captions. And these are fairly popular tasks with many systems submitting. So this is actually a new figure. So this is just kind of like where things are currently in 2020. So sentence embeddings are, you know, kind of, you know, not as popular as they once were, but there's still lots of sentence embedding models available, especially now with like BERT. People have been building sentence models like Sentence BERT, which people may have heard of. But in these tasks, it's still the case where, you know, despite these evaluations have been around for a while and used in all these papers at some level, this simple model that I'm going to describe next is still state of the art by like a strong margin. Once it's, you know, brought up into the same setting as these other ones, i.e. same dimension, and, you know, you train on 10 or 20 million sentence pairs. So like this similarity model, you know, is on the far right. It's the TAN model, that's ours, what I'll describe later. But it still has very strong performance compared to these modern methods, and models. It also has the advantage of being super fast since the encoding function is so simple. And these have been used for, you know, helping with review assignments and stuff recently, as well as clustering similar papers. And so it's still like relevant for today. And I'll just quickly get into like how we can learn these representations. So I've already kind of discussed our model, our discriminative model, and I've discussed some of the data that we could possibly use in Paraphrase Database. But there are many different other settings that you can do that are, you know, very similar, but give you very different effects. So again, you can use PPDB though for this level at the sentence level. Essentially though, you're dealing with short little phrases. I wouldn't even call them phrases, they're more just like snippets of text. But there's millions of them, and they tend to be have some enough high quality ones in here that you can actually learn very strong models. So our objective function then with these are exactly the same as in the word case. The only difference now is our G is a little bit more complicated. Instead of being a word lookup table, it's, you know, again, looking up the word embeddings for the underlying sentence pairs, but then it's also composing them in some way using a different composition function. But otherwise than that, it's the same kind of game where you're doing this max margin and contrasted loss over the positive examples in the data. So, you know, just this composition function is, you know, what I'll talk about just real briefly is that it's, but basically the G is just, you know, again, you're getting these word embeddings, and then you just do this G function to sort of, collapse them into a representation. And so like the simplest possible representation, simplest possible G here is just to pool these underlying representations. But in later work, you can get it to work with things like LSTMs or transformers. And the last thing, I mentioned negative examples earlier. The thing about negative examples is like how to select them is actually very important. If you do random, which some papers do, what happens is like you don't tend to maximize performance. In fact, you get kind of very basic performance because they tend to be too, especially in the sentence case, they tend to be too basic. So it helps to really find nearest neighbors, and those are then your negative examples. But you want to find these nearest neighbors over a large pool of data. So what we would do is, like, to make it efficient, is what we would basically collapse a bunch of batches together into like a mega batch. Usually like 40 batches or so. And this had a drastic effect on performance, increasing it by about, you see in the chart, it can increase it by about 4 points or so, which is pretty significant. And you can kind of see on the left, you see the table with the negative examples, and you can see just how if you just do a batch size of 1, it's like not even that related. But as you get to like, as you start collapsing into 40 batches, then you get things that are, kind of, they have, the meaning is much more overlaps, providing a stronger training signal. So I alluded to, our initial G function of just pooling embeddings, and that's kind of what we ended up with. But we did try lots of different models in our first iteration of this, our first iteration of our goal of trying to match this performance of these trained systems. So essentially, like, what we found to work well is just averaging word embeddings as shown in this figure. But we did try a bunch of other models. So this figure shows, like different approaches. We have GLOVE, we have our Paragram word embeddings, which you can just average. We have LSTMs. We have models based on learning a projection matrix and then averaging. And we just found that essentially just averaging in red is, first of all, it's very similar to projection because they're both averaging. But the most important and more surprising thing is it outperforms the LSTMs. And that was actually very troublesome in a way, because we had thought that the LSTMs would do best because they're able to capture word order, and simple averaging models can't. So we came up with a bunch of hypotheses like why does this happen? We basically explored these things like, is it because of their short sentences? Is it overfitting in domain? Did we not tune it or optimize it correctly? And we investigated all these exhaustively, and the answer to all these is no. That is not why. And so like this was an open question for a little while, but we'll again come back to this a little bit later in the talk. Again, did these models have other use cases besides just, being useful for like unsupervised paraphrase detection? The answer is yes. You can use them for fine tuning. You can use them as features. We did both, again, in our original paper, and found them to be useful. Here's basically a fine tuning setting. And then the other question is, why do these work? Since you're just doing a simple averaging function, and a lot of the power is in the norms of the vectors. Essentially what it's doing is it's like basically recalibrating the norms to fit with being like reflecting the importance of the underlying token. So here, like the number 18 is actually considered quite important by the model because it's very specific, and it's something you want to match, pretty precisely. But of is tend to be, since you're not really factoring word ordering, the word of has like little semantic content. So if you compare from like GLOVE to Paragram phrase, the norm of 18 increases significantly, but the norm of actually decreases. And then as a follow-up work, we noticed again another, in analyzing this, that there's a large effect of having out of vocabulary words. And so that was something that we had tried to address in our into our next paper, which I'll just talk about real briefly. And that's these Paragram embeddings, where you basically, you kind of ignore words. And what you do is that you just have an n-gram model 3, 4, 5, 6 character n-grams, and then you just sum them up, and you add a bias, and you do a nonlinearity, like a little baby neural network, and that's how you get the representations. What it looks like is for sentences, usually trigrams work really well, and all you do is you just kind of have a, you keep the space in the beginning of the sentence. You incorporate spaces in as part of your vocabulary. So you just kind of move this window across your entire text. Each character extracts a new embedding, and then you pull them together. But this led to significant gains. So on our STS performance, our Pearson correlation, it improved over our word baseline. For word similarity, it was even bigger, just by, again, having a set of word embeddings. We just have these character average embeddings. Fast text came out after this, and they basically do a similar thing using n-grams. So it's just kind of nice for making these word embeddings that make them more robust and handle outside domain data better. And they can also just be used as well as for like downstream tasks, like these hierarchical LSTMs were popular, where you basically have an LSTM with the characters and then another LSTM that takes those representations and then runs them over the sequence to predict the tags. But you can stick in these Paragram embeddings, and the performance is similar, but the convergence is much faster since the model is there's like just a heavier inductive bias, and it makes optimization easier. These are also capable of handling negation, which is kind of interesting. They are able to handle some kind of compositionality. Essentially, like the nearest neighbor for the phrase "not capable" is incapable, which is sort of surprising and pretty interesting, actually, considering that the only link between composition here is like a single trigram. In this case, the trigram between T space C. And then most importantly, they're able to model slang and misspellings and everything. And we get strong similarity even with this, even despite having 0 character overlap. Like the bottom example with huge, huge and enormous don't really have any character n-gram overlap yet. That's the nearest neighbor for huge. So that's not a worry with this. So now that I've talked about the simple models, I'm just going to get into how can we get these deep models to work? LSTMs didn't work earlier. How can we address this? Is it possible to get these to work in this kind of setting, or do we need to have a new setting, a new training setting? And so what we started to do is we started to like play around with sentence paraphrases. We found this resource called Simple Wiki, which is basically Wikipedia mapped to Simple Wikipedia, which is essentially a Wikipedia that's written for people that are, for people in grade school or people that are new to English. It's just a simplified version using simpler vocabulary and shorter sentences. But it's a source of paraphrasing. And so we experimented with that. And we also experimented with recurrent networks that we tried to make them as close to averaging as possible. So essentially we had this gated recurrent averaging network, which is essentially averaging, except you have a gate that's conditioned on the past here. That's the sequence in the sigma symbol. And that kind of controls what aspects of the word embedding are included in the average. So we just kind of try to, start slow. Can we, if we use sentences, is that different? How did these networks that we try to get very close to averaging perform? And so what we found actually so in blue here, this is actually PPDB, where we just do our word averaging model and our LSTM. This is from before. But now on the simple wiki data, matching the data for data, the LSTM increases a lot, which was very interesting, even though the word averaging only increases a little bit. And then we found that if you add regularization to the LSTM, such as like you scramble the words a little bit, you basically add some noise, like a denoising autoencoder kind of thing, and you add some dropout, you can actually now match the performance of the averaging model just with these few tricks. And then the GRAN is a little bit better. But essentially, this comes down to that it is, this is like the real reason turned out to be that the data we used The text snippets, it wasn't handled well by the LSTM, but needs sentences to learn from. So, but people don't really write paraphrases. So getting paraphrase data at scale, like we could for PPDB, is a bit of a problem. Resources like SnpWiki and stuff are limited in size, and they're limited in domain as well. But people do translate a lot. And so we just turned to like using parallel data exactly. And parallel data is ubiquitous. It's ancient even. And new sources of parallel data are created all the time. Things like parliament proceedings, news articles, movies being translated through subtitles. So we settled on like structures of parallel data. We picked was this parallel corpus called Seizing. We liked it because it's huge and it also contains data of like a variety of domains, things even including medical or fiction even. But it's mostly like EU legislation and subtitles, but it does contain some more niche domains. And then the question is, how can we, create a paraphrase database from this? So neural machine translation systems were new at the time, but they were, having quite impressive performance. And so all we did was we took the winner of the WMT 16, and then we translated the Czech sentence into English, and then we kept the English reference, and that was our English-English paraphrase pair. So we're only generating one sentence, and the crux of why this actually works well is like a lot of these translations are translated kind of liberally, where like they're not exactly word-for-word translations of the underlying English, and so like this is really nice then when we're trying to find paraphrases, because then if you translate things exactly, you're still going to get a nice paraphrase. And then using this NMT, and you filter a little bit to remove the noise, i.e. translations that don't work, or sometimes there's unalignments in the translation data, but you just remove that stuff, which is pretty easy to do. The performance matched SimpliWiki on our averaging and grand models. Moreover, we investigated other common corpuses like Common Crawl or EuroPearl. And we just found Seizing to be far better once you do an apples-to-apples comparison. And this table just shows like the quality. Naturally, in paraphrasing in general, there's a relationship between paraphrasing quality and diversity. And this just shows that, as you get more diverse, the paraphrase quality decreases. So the diverse is like this, measured by this trigram overlap. So most diverse is at the bottom, and most diverse is at the top, and least diverse is at the bottom. But essentially, there's a sweet spot basically around, in the middle of this table, where you get a mix of both diversity and strong paraphrases with just a little bit of noise. And this is useful for other things besides learning embeddings, as I will discuss very briefly, but it's also useful for paraphrasing. And just here are some examples just to show that like these don't line up as close as you might think if you look at embest lists and stuff like that, just due to the nature of the underlying corpus. So, now that we can create this corpus and we did it at scale, we made a corpus of around, that Seizing is around 50 million, so we made about a 50 million corpus, and then, filtered it a little bit. Then we evaluated just our basic models. So here we have the STS Competitions. This was the winning system of each year is in blue. This was like our long-term goal that used the training data, and people like incorporated other resources and tried to win these competitions. And if you average glove, that's kind of where you start off with. That's in green. So that's kind of, a natural baseline. But just now by training these averaging models, over this data is enough to actually significantly beat these winning systems. Again, all you're doing is averaging, but this combination of this corpus and our models is enough. So that's it for that. Now I was trying to briefly move into the multilingual space. So now we did this back translation step to get these paraphrasing embeddings. The natural question though is, what is this needed? Like, can you just use the multilingual text directly? what happens if you just do our training method with just that. And that's what we did as well. So we basically then moved into this cross-lingual similarity setting. So the two bars on the left are Arabic, Spanish, Spanish. But then we also have cross-lingual. So we have Spanish, English, Turkish, English, and Arabic, English. And these were the winning systems for, there was another semantic similarity contest in 2017 that focused more on multilinguality, or more likely cross-lingual, since it's only two. So here we essentially we're using sentence piece by Google instead of character engrams or averaging words. We use this segmentation because we found it to be comparable to character engrams, but it's much faster and quite a bit simpler. So yeah, so this method works cross-lingually, where if you just get multilingual data, Arabic data, you just take Arabic English data and you just train these models. You get models that are both good at Arabic and models that are good at English, as well as cross-lingual similarity, as shown here, like Arabic English. And it's very competitive with the winning systems, except for Spanish English for some reason, which I'm still not entirely sure why that model was so good. But yeah, so it's effective. The other thing is it's very fast. So people might be familiar with like Laser from Facebook. This is like Schwenk et al., where they trained LSTM. It's for do translation, multi-way. If you do an apples-to-apples comparison on that using Europarl for like English French and English German and mining by text, our models are quite similar in performance. But the thing is that they're much, much faster. So you can do, this is how many sentences you can do per sec encoding wise. And so you're talking, like, a couple orders of magnitude faster. So if you're mining by text, this is something you want to do probably because you're going to want to encode lots and lots of sentences. Now I'm going to talk about something that's more recent and a bit different than these simple models. And this is, a generative model. So essentially, I mentioned early in the talk that we have these two views of language, and this is kind of making that more explicit. But now the different views are coming from other languages. So if you have English French text, you could say that you have two views. One is the French view, and one is the English view. And so what we were after here, we were after essentially taking what is common between these views, and that would be our interlingual representation. And then as a result, we kind of filter out the aspects of the views that are very specific to those views, i.e., like information responsible for French variation or information responsible for English variation. So these are all more trained in the NMT setup. Essentially, you have an encoder and a decoder model that tends to generate the text. But the decoder is only conditioned on a single representation from the encoder. And so here we use transformers. And so what we had to do is we had to figure out, where do we put this representation in the decoder, among other things, because it's like, it's built on this source attention, which now doesn't exist because you're just essentially using this vector. So we did some things here to figure out the best way to do that. And like these were baselines, that didn't, this was like work that had a little bit been done by others, but like they hadn't really, they kind of just did it in a very basic way, and there's a lot of room for improvement. So for example, in the LSTM case, you have this encoder decoder thing model, and what most people would do is they would just take the initial hidden state of the LSTM and the decoder, and that would be where they put the representation. But we found that like if you kind of play around with LSTMs, you find that this pattern where the semantic similarity performance of the models, and this is also true for other tasks like sent to val and that kind of thing. Performance that generally goes up the further in the network you go. And this tends to be because of, that's also where the loss function is. So this is essentially, helping you with getting a more direct feedback during the backpropagation. It's not having to travel through this entire network and many operations to get to your representation. It can just hit your representation very quickly. And so we found that this was very important to do. And then similarly for the transformer, we had to figure out where to, where this goes. And so I'm not going to talk more about this in the details, but essentially there was this relationship also between encoder layers and performance. You want the decoder to be very weak. So one layer decoders are good, and encoders, the stronger they are, the bigger they are, which is kind of something you'd hope for in this setting. It's true for things like Birch, but it's also true here. And then lastly, like batch size is very important. The model doesn't work at all unless your batch size hits at least 25,000 tokens at minimum. So this was another thing that's kind of important in an engineering perspective. But then back to this model. Basically, this is our latent variable model, and this is our generative story, where essentially we're saying that you can generate this translation pair. You basically have 3 latent variables, one for responsible for French linguistic variation, one for semantic, the shared semantic variation, and then one for the linguistic variation specific to English. And then to generate a translation pair, you generate this shared semantic variable first that's responsible for its meaning. And then you condition on that and your French specific variable to generate the French side. And similarly, you condition on the semantic variable and your English variable to generate the English side. And so that's kind of our setting is, and our hypothesis is that the shared semantic variable, once you use that, that is going to help you a lot with these semantic tasks, because the information that's shared between these two views should be information that is semantic in nature. So how do we learn the representation, the parameters for this model? So, ideally we would like to maximize the likelihood, but however, this is kind of this typical VAE setting where the integral is intractable, and therefore we optimize elbow, a variational lower bound, on some approximate posterior that we introduced, Q, which has its own parameterization. So this is kind of how it looks like. So we factor our Q distribution as a product of 3 distributions. And each of these have their own inference network shown on the left, one for each language. And then these inference networks, they will output the mean and covariance of each of these factored Q distributions. And then these distributions are used to sample points from the latent space. And this allows us to compute the first term in elbow, the expectation term here. And then the second term in elbow is this KL term. And this is responsible for the source separation that we're trying to do. We're trying to separate basically language-specific information from shared semantic information. And so this is pushing the Q distribution towards the Gaussian priors. And it's basically what it's doing is it's encouraging the variation that is shared by the translations to be explained by the shared semantic variable, and language-specific information to be explained with the corresponding language-specific variables. So if information is shared by 2 sentences, if information is shared by both like the English sentence and the French sentence, it's cheaper from the KL perspective to put it into the shared semantic encoder, because you only pay the KL term penalty once. But if you put that information that's replicated in both sentences into their respective language-specific encoders, then you pay the penalty twice. So this is kind of how you're trying to motivate this disentanglement to happen. And then from a computational perspective, it's actually quite easy to optimize this. You basically stick in your English and French sentences into their encoders. You run to the network, you collect the means and the covariances, and then you use the reparameterization trick so you can backdrop all the way through to sample from the space. And then you basically just have these decoders then that conditioned on your sampled Z variables. How does this work then? So how does this perform? So we took, work from the literature, work from our earlier models, like the sentence piece models. The translation model is shown in purple. Here, this is our, our highly tuned translation baseline. But then adding this source separation stuff with our model, the BGT, the bilingual generative transformer, it has significant improvement gains due to this, what we hope is this source separation. And to also measure, one of the weaknesses of our earlier work is this inability to reflect word order. We created this like hard STS data set where essentially we looked at sentence pairs that had very high overlap, but actually ended up being negative. And similarly, whereas at a very little overlap, that ended up being positive, like in the first row. So on this data set, now you start to see like the effects of being able to capture this word order. And this is something that was a little bit surprising that some of these prior works weren't able to do this well either, since they are usually LSTMs. But for whatever reason, they cannot. And these models, there's not really much interesting translation of BGT here, but it kind of shows that you're on the right track of being able to model more complicated sentence structures. Cross-lingually, they do very well compared to the translation baseline. This is kind of a reflection of the source separation that's occurring, because once you start stripping away this language-specific information, these sentence embeddings should be in very similar spaces, despite being from different languages. So the gaps for things like Spanish, Arabic, these are smaller, but still significant in favor of BGT. But then once you get to cross-lingual settings, the gaps widen considerably. And then, are we actually doing source separation, which is, what we've been proposing this whole time, but it's important to verify that this is happening. So we tried some probing tasks. Essentially, we took the English-specific language encoder and our semantic encoder and our bi-trans model, our translation baseline, and we just looked at how they do on these various probing tasks. And what we found is that there's a difference in what language you choose. So we used French for most of this paper, but we also tried Japanese. For French, you start to see where the semantic encoder is capturing more semantic information, like predicting number of subjects and predicting number of objects. It's outperforming the translation baseline, but more importantly, it's also outperforming the English encoder. But for Japanese, it's a little bit different, where for subject and object, the English language-specific encoder is actually doing a better job here of incorporating this information. Similarly for syntactic probing, for French, in this case, the English-specific encoder is worse, but for Japanese, it's a little bit better. So, why is this happening? Essentially what's happening is, like, for English and French, there's a lot of shared structure in these languages. They tend to share things like this information. And so that information is now being put into the semantic encoder. But for Japanese, since the languages are so different, the English-specific encoder has to work harder. And therefore, it's the one encoding this information. For other probing tasks, we find that there's a little bit of a reversal here for certain things like punctuation, length, favoring the English-specific encoder, gender. Since French is a gendered language, you can look at what's, which encoder is responsible more for predicting gender. So we found that to be the French language encoder. And then for Japanese, it's, again, the language-specific encoders are doing more of the heavy lifting here. Since they have to essentially be able to reconstruct their language in full, since there's so little shared. But you still get really good performance no matter what language pairs you use on, like, the STS, because there seems to be some latent semantic meaning that's being kept across. And then you're able to do a little bit of style transfer, which is kind of interesting. These models are very generative, so you can generate from them. And what tends to happen is, like, whenever you feed into the English-specific encoder here, like the style, it has that structure. But when you feed in something from into the semantic encoder, it usually carries over the subject from that, and it just kind of tries to fit it into the style vector. Sorry, into the output. And And then real briefly, I'm just going to talk about machine translation. So essentially what we have is, in our model, we have these paraphrasing representations, and they're very useful for things like detecting paraphrases automatically. But we hypothesize that it can also be used as a reward for fine-tuning generation systems, like for MT. And so in MT, most people use maximum likelihood estimation for solving the translation problem. And to fine-tune these models, they use BLEU, since that's what's used for evaluation. And set this level of BLEU more specifically, since BLEU is very sparse at the sentence level. And so how this is commonly done is people can use reinforce, or you can use minimum risk training, which is quite similar to reinforce, and they're both, optimizing the, in a sense, the expected cost or reward, but they do it differently. And in minimum risk training, which we use, and it seems to work a little bit better for us, but I think it's very debatable. But essentially, what you're doing is you're creating this. You're essentially sampling many hypotheses at once, and then you're renormalizing their probabilities to create your expectation, and that's what you're using to. Then you can backprop through these through this expectation, because you have these probabilities are all differentiable. So what do we use as our reward? Well, we use our, our best similarity model. This is pretty well tuned for this, because it's very fast. So to do reinforcement learning, you need to be able to very quickly compute your rewards, but you also need something that's very effective on the semantic setting. So this seems like an ideal fit. We made one modification. Essentially, you want a length penalty. So BLEU has a length brevity penalty. Here you want a length penalty where you want to keep it from being too long or short. So essentially, you just try to keep it relatively, there's a penalty that basically penalizes how much it deviates from the reference length. So we have a recall-based metric. So unlike BLEU, which is precision-based, BLEU, you kind of, without the brevity penalty, you get you benefit from making your sentences shorter and shorter. For our case, you actually benefit from making them longer and longer. So that's why this penalty is very important. And then, a little bit more of an analysis of using BLEU, like why something like this would be effective, is that essentially with BLEU, there's a lot of repetition. It actually turns out to be a very discrete metric if you do a histogram plot, where if you sample like 8 candidates for each sentence, there's a lot of repeated scores. About 15% are repeated or so. And you get this histogram that's kind of steep. But if you use, something like our metric, our post metric here, similarly, the repetition is very small. The curve is much flatter. And we hypothesize that this gives you more of, it makes hill climbing easier. It basically gives you more information on how your hypothesis is different. And so it'll help in optimization. Moreover than that, these are common issues with BLEU that I'm sure everyone knows about. Very small deviations in text cause large effects on semantics despite little changes in the BLEU score. So here are outputs of our risk BLEU, our risk simile for different settings. So here, there's information missing in the risk BLEU case. It's not reflected in the BLEU score, but it is reflected in the sim score. Here there's a contradiction, again, not reflected in the BLEU score, but it is reflected in the sim score. And here's a case where there are, both sentences outputs are fine, but the BLEU scores are drastically different, kind of giving a confusing signal to the outputs. This just shows that simile is not affected by the length penalty, doesn't really hurt you. And here's our training setup. Essentially, we just use WMT, but we use a smaller pool of data. We did 4 languages just to try to maximize experiments to try to be as convincing as possible. And then we use this convolutional encoder-decoder models. What ended up happening then is for automatic evaluation, you actually do better on both BLEU and our semantic similarity reward, which also can be used for evaluation, no matter which essentially, if you use risk with simile, you get gains in blue and similarity. And it's a little bit surprising to get the gains in blue since we're not optimizing for that. But it tend to happen, and it happens significantly for all language pairs. So here's Czech and German. There's also Russian and Turkish, where it happened as well. More importantly, in human evaluations, these were favored too with our simile objective. Blue, it didn't work quite as well. The one exception here being Turkish and English. And then a natural, issue with this was that we didn't do it on transformers, and we didn't do it on really heavily fine-tuned data. And so we also, now we've done that. We've done those experiments, and like the same thing holds. Here's cross simile, which actually uses the underlying German as well, which has gains. These are all significant with the asterisks. So this works on even state-of-the-art models. Here's evaluations according to sim. Here's evaluations according to cross sim. So this does have and here's human eval outputs. These are little asterisks here because I did filter these by the most different. So I took so the human evals are a little bit exaggerated just to make most use of the higher translator's time, but there's still gains here, statistically significant gains. And then again, kind of reflecting, convergence. Convergence is much better with this model, which is kind of what we hypothesized with basically giving more information across the candidate lists. Whether you're measuring the convergence by the expected blue or the expected simile, it's the same thing for both models. And then we also found that it tends to favor, just like we talked about with Paragram embeddings, they put higher norms on words that are more important. And that's the same thing too, where you're more accurate in predicting words that have more semantic content, like nouns or numbers. So yeah, so fine tuning with these is actually quite interesting. It leads to both increased performance and even including blue score, which was not a goal. And it results in easier optimization as well. So you don't need to train for very long to get good effects. And it seems to be very robust as well to random seeds and everything. All experiments were run 3 times, averaging the results. So, and then future work, I'm sorry, I'm running out of time a little bit, but one thing I'd like to talk about is just for future work, I'm very interested in paraphrasing. Again, I did some work actually with Mohit Iyer, who was at AI2 at the time, on generating paraphrases with control, where you essentially specify a parse structure through use of just the top level of the parse tree, and then you can generate paraphrase with that structure. What I'm actually mostly interested in now is essentially generating very diverse paraphrases. So one way to get diverse paraphrases is through the syntactic controlling structure. But what can you do? That was largely syntactic. There's also lexical as well and different styles. And so there hasn't been much work in this area, and I'm happy to talk about this more, but hypothesis can be used for style transfer and for augmentation and robustness. I think this is something that's a little bit unexplored and could be very useful. We do have a little bit of preliminary results on playing around with this, where this diverse paraphrasing kind of messes up the original sentence space, allowing some text normalization, which lets you do style transfer in a different kind of way. So here's some examples that we kind of have already. Tweet to Shakespeare, poetry to Bible. So these are pretty impressive, and this is just kind of a starting point but it all hinges on this diverse paraphrasing where you can renormalize the text. Other things, there's a lot of room to gain, I think, on both automatic evaluations and training, MT models or summarization models, or story generation as well. There's probably a significant gap between human performance and current approaches. I have some ideas on how to address this. It'd also be interesting to see what a human reward would do for MT. Like, how much room is there to gain? Because I was pretty impressed that reinforcement learning doesn't seem to work that well for MT, but when you use blue score, but when you use these other rewards, it does open things up quite a bit and make it much easier to use. There are some papers out there that kind of doubt MT minimum risk training improving at all, but it seems to be very robust if you use the right kind of reward. So that's another question is, this kind of go hand in hand, like automatic generation of automatic evaluation, and then also fine tuning these models. And then lastly, again, kind of corresponding to these is like, I think that these might be important for things like text generation of different scales, translating books, translating articles, making things coherent on a long time scale. I think this additional feedback from such models in some kind of a reinforcement setting, perhaps with properly crafted rewards, might be a way to attack these. And this problem in general, even other alternative strategies, I think this is something that would have a lot of impact. And so that's one way to attack it. I'm sure there's many more. Okay, so thank you. I'm going to close there. But again, basically, I just wanted to point out that we have these effective strategies for learning embeddings with different granularities. They range from fast to more complicated, and they are very useful for even applications like fine-tuning NMT systems. So thank you.
All right, so let's unmute and give a round of applause. So, very interesting talk, but we don't have a lot of time left. Any questions from the audience?
I have. Oh. Okay, go ahead first.
I have one question. I'm Yinhan from Incubator. So I was wondering, have you tried to use Paraphrase to do pre-training?
You mean like Elmo style?
Like a board. So before I left Facebook, I did a little bit, but that was really expensive. But I tried to translate a round trip translation from English to German, then German back to English, and translate the entire book wiki, and then use that to do pre-training in the same style as BART. I don't know if you have a chance to read the hard BART.
Yeah.
Yeah. So then after that, it was able to match BART result on Matanoa actually, on the base BART, but it's really expensive to do the entire corpus for the BART large, which is like the robota data. But so it's now soda, but I wasn't an expert in this area, so I just used like a bin size to do the motion translation, but I didn't control the diversity. So I was wondering if the diversity was controlled very well. I don't know, probably the pre-tray, so the classical pre-tray is like adding noise, then denoising. So Paraphrase, I feel is like a very interesting field to do pre-tray. I don't know. I mean, I never tried on the entire course.
I'm interested in it. I haven't worked in it largely just because there wasn't resources to do that kind of thing. So I never really got into it. I feel sometimes I know sentence embeddings are a little bit less popular and favor these pre-training approaches. But yeah, I do think I think it'd be very interesting to actually explore something like this. Even like if you think about it at the sentence level, like most of these pre-training approaches are at the word level. Are there gains if you actually move to higher granularities of text, like sentences or multiple sentences? Can you do something more there? Like, is there information there that might be useful for like tasks that use sentences? Like, for example, like on like evaluation and that kind of thing. And but yeah, I agree. It's expensive and it requires a lot of scale. But I think it could be an alternative approach, which I think would be kind of cool to explore at some point.
Okay, would you like to go next?
Yeah, I'll ask a quick question. So I find it's very interesting that you mentioned your future work, you want to do this kind of like syntactic style controlled generation. So I read the SCPN. I think it's very interesting to kind of like having the syntactic structure there. I'm just wondering, like, do you think like non-autoregressive models could be a better fit when we want to incorporate like syntactic structures? Because when I read SCPN, it feels like when we first sample like a syntactic tree and then generate like autoregressively from left to right, it's hard to kind of like make sure that the generated text follow the syntactic tree we sampled. And I wonder if you have some more insight you could kind of like provide, what's the next step to kind of like tackle this kind of questions.
So I agree that yeah, generating in order from left to right is definitely a little bit of a difficulty. I mean, we are tending to the parse, so like it should kind of know where it's headed, just like in translation, where you kind of have to know where you're headed. But I agree that it's a little bit more of a global problem, and so like a non-autographed approach is clever, and I think that might lead to gains. But the SPN results were quite good. They tend to follow the parses even without that. What I was more interested in getting into there was just the fact that you even need parse templates and everything. It'd be very nice if you could just kind of set a parameter about how diverse you want to be, and the model will output plausible paraphrases that are quite different from each other, both syntactically and lexically at the same time. So kind of removing that step of needing an exemplar or needing, needing parse templates, which have a weakness in that sense where you might not be able to actually make a paraphrase with that template. So it just kind of removing that step was something I was more interested in doing.
Oh, I see. So more like an end-to-end model in this case.
Yeah, more end-to-end, and just kind of being able to set some parameters for how much you want, like how much diversity you want.
Yeah. I think that's a good idea. Okay, thanks a lot.
Yeah, thank you.
So I would like to mention that people who need to leave can leave now, but thinking that maybe let's do QA just a little bit more. And then the next interview is Swapa, but next is me. So I think we can shift the time around a little bit. I want to ask a quick questions, two maybe related questions. I really liked the generative models where the semantic is being shared across two different languages. When you are doing the STS type evaluation, what exactly were you using as the embedding? Were you using the Z or combination of, I mean, like which Z, if Z?
Oh, yeah.
And did you try like using different portion of the learned embeddings, and how does that influence the performance?
Yeah, using we actually just used the mean, the mean vector. So it's just kind of like the mode of the distribution that we're trying to learn. Because adding Z's, it just kind of adds a little bit of noise.
I imagine that it's really hard to learn accurate Z, and in the end, so you are using the X embedding, the text embedding. Interesting.
And we just used the semantic encoder then. We kind of threw out
So you're hoping that by having these latent variables around, you still learn meaningful representation of X. Although ideally, we wish that Z themselves are that meaningful as well. No?
Well, I just look at the Z's as more like, there's like, they're more like points around. I mean, you could.
I mean, especially when you combine the semantic Z with English Z, don't you expect that they together should be able to reproduce the original X English?
Oh, yes, and they largely are able to actually, like in the generative.
Yeah, you can reconstruct. But then when you are doing this STS evaluation, it sounds like you're using the representation of X directly as opposed to representation of Z.
I'm basically just using the mean, which mainly is just due to make things kind of like robust as well, since there's no like sampling involved. It's like you get the same results every time. If adding a little bit of noise, the results are similar, but you use different results every time you run, depending on how you sampled the Z's.
So yeah, the real question that I wanted to ask, which is somewhat related, is so you're talking about the style transfer using it in the end, but not quite a bit about actual paraphrasing performance based on this particular work.
There's a misnomer there. It's much more just show like another that there is.
Yeah,
like,
that's cute. But do you have you tried doing paraphrasing also from this representation, or is it just not as straightforward compared to your other previous paraphrase?
The problem
models?
with like paraphrasing and generation from these models is that they're kind of poor at it, since like they're just kind of conditioning on a single vector.
Yeah.
It tends to weaken them a lot. They have a lot of difficulty with like more lengthier outputs and stuff like that.
Yeah.
If you train them at scale, maybe this would, be less, happen less. But even with like VAEs, like they don't really reconstruct all that well.
Yeah, that's
you kind of have that problem with these as well. So there's a little bit of paraphrasing going on, but I guess in general, I'm a little bit skeptical of paraphrasing models that use latent variables. Maybe some are very effective, but like it just seems to be kind of a
variable there. You mean latent variables?
Yeah, just one's trained with like a with the reparameterization trick and everything. It just seems to like really kind of hurt your generation outputs.
There's this work I've seen that uses VQVIE for paraphrasing without bytext. I don't know if you. Maybe we can take it offline. But yeah, any other questions?
The paraphrasing literature too is a little bit problematic, where you can have papers that are. I mean, I don't know this paper in general, but I'm just saying as someone that's reviewed a lot is like, you have to be very careful in how you, because there's no real like stringent comparison evaluation.
Yeah, and
people tend to
a lot for that purpose. But on the other hand, is it even proven that system that does better at STS actually does generate better?
No, they're actually very unrelated, because like you can't generate like those like contrastive losses and stuff.
Yeah.
There isn't really a relationship, but like the STS thing is more about how we were representing the composition of language, and we chose it because it was convenient, but it caught on too, so it has some a lot of people have been doing it, but I agree, like better evaluations would be very useful, especially for paraphrasing too. Like the paraphrasing literature is actually kind of a minefield of people doing different things, and it's just hard to compare to other.
Any other question from the audience? Sorry, Swapa, I'm like eating into your interview slot.
That's all right.
I can trade time though, so that's okay. No more question? Last chance. Otherwise, we'll thank the speaker again.
Thank you so much. Sorry, I went over a little bit.
All right, so Swapa is next, and then Swapa, you can use how much longer you like, and then I will go from there.
Okay, thanks.
Just let me know. Just Slack me afterwards so that I know when to log in.
Sure.
Okay,
all right.
bye.
Okay, bye.
Thank you.
I don't know if John needs to take a break though, briefly.
No, I'm okay.
Yep. Okay. Talk to you soon. Bye-bye.
Link. Yeah, see you soon. This one.